All right, so if I have an aircraft, we had the F4, right? It was the F4. Now the F4 is a MIMO system, multi-input, multi-output. It has elevator, ailerons, rudder, flaps, whatever. You have all these inputs, and they're going into the way we model the aircraft. That model is always MIMO. All practical control systems are MIMO. So you have to realize in 320 you're always looking at subsets of some MIMO system. But now we're going to actually look at the MIMO system. So our MIMO system can be displayed in 2 or 3 different ways. One way is the state space form, which you should have at least been exposed to, right? State space. If not, you look at Nelson, the state space form shows you how to model using stability derivatives. If you linearize the equation, you get a state space form for the longitudinal mode and a state space form for the lateral mode. Or you could use transfer functions. Transfer functions you can get from state space using that formula, C, quantity Si minus A, closed quantity inverse B, CAV. The C, Si minus inverse B will give you the transfer function. Or how do we do that in MATLAB? SS2TF, right? SS2TF does this for us in MATLAB. Gives us the transfer functions. Or you could use Archangel. And if you use Archangel, you'll get the Kramer's form, where numerators and denominators in the form that we were used to seeing it. Where we have a numerator over a characteristic equation, one for the longitudinal mode, one for the lateral mode. In the longitudinal mode, the phugoid in the short period will be embedded in the roots in the longitudinal del. Right? With me? Any questions on what I'm doing here? So it's MIMO. And then out come these variables. In the longitudinal system, I have airspeed, angle of attack, Q or theta. The integral of Q would be theta, or the derivative would be Q, of theta would be Q. Now, here's the question. I want to stabilize this system. I want to stabilize. So I'm going to feedback Q. Now, how do I know to feedback Q? Well, from experience, basically, and I found this book. This is probably the best book ever written on aircraft flight control. It's written by McClure, Ashkenash, and Graham. They're all dead now. I knew them. This book was written in the 60s from Northrop on Century Series fighters. It's a great book. It's hard to read. It's a very demanding book, but it tells you if you want to stabilize longitudinal mode, if you want to stabilize lateral mode, what do you feed back based on experience and analysis, all in this book. A lot of the problems that I've seen when the Swedes build a Gripen or another, someone builds an airplane and they don't use this book, they violate one of the rules, and then they get a pilot-induced oscillation, or the aircraft doesn't do well. So I'm going to get this back to the Flight Sim Lab. This is my old book. Hopefully I duct taped it together a little bit, it lasts a little bit longer. But this was my Bible when I was learning it, and it still is. It's kind of like Roxton. Everything in here is good stuff, if you can understand it. But how to close the feedback loops is pretty straightforward. So we're going to close Q to rate stabilize the longitudinal mode. And notice how I put the minus del E as my variable. I picked minus del E because that's a pitch up command. A pitch up command, by convention, is a minus del E. Everybody follow that, all right? Because if you don't do this, you're going to get the wrong root locus. You'll get a wrong root locus. You'll get a root locus between even pole, to the left of even poles and zeros instead of to the left of odd poles and zeros. So this is a necessary step for a pitch up command to give me Q. So Q to minus del E is going to have a positive sign, as you saw in that video. And that Archangel takes care of it for you. It does it automatically. Then I'm going to feed back Q, right? And what is this system then going to look like through my actuator from Lab 1? Well, we know from last week that this part, this forward loop part, is given by this matrix, this Laplace transform matrix that we did last week, except I've added the actuator now here on the input side. But this is the Laplace transform of the linearized equation. So if I wanted the solution from Q to E, which is E is the input to the actuator, then what would I do? I'd take a numerator term, which would substitute the Q column with the B column. So I take the B1, B2, B3, and I substitute it for A13, A23, A33. That would be the numerator. And I call that NQ delta E. Yeah? That would be NQ minus delta E, would be that guy right there. And then the del would be the determinant just in this guy. So Q to delta E, we know how to, we did this last week. Now what happens to that when I feed back Q? Well, this E over here becomes Q command, and I probably should put command there. This becomes, I'm just renaming this, Q command minus KQ Q. So E becomes Q command minus KQQ. So if I were to substitute Q command minus KQQ for E, or GX rated times E, I'm just going to do this substitution, then I can see that this is going to break up my right side into two terms. I'll have one term over here, B times QCOM, and I'll have another term, B times GX times KQQ. That Q term, I will take that column and put it into the third column for the closed loop. So when I close the loop, this third column I move from the right side into the left side, and this will be your loop closure for your inner loop. That'll be your loop closure for your inner loop. Okay, now you can do this at home and see how it works, see how it works out. But look at the solution for the numerator for Q to QCOM. How do I get the solution from Q to QCOM? I take the determinant of this, right? Do you see that the determinant of the closed loop is going to be different than the determinant of this? Do you see it's going to be different, right? So I have new closed loop roots. They're going to be stable now. Those roots will be stable now. Zach, you with me? Look like you're dazing off. Okay, you with? All right, so this is different than this. These are the closed loop roots. But look at the numerator. How do we get the numerator for this? I take the B column and I substitute for this. Right? Is that going to be any different when I take the B column and substitute for this? The third column is gone. The third column is gone. So I'm going to get the same numerator I had before. What does that mean? The zeros are not going to change. When I close my loop, the zeros are going to stay the same, right? The zeros are going to stay the same, and I have my same numerator transfer function. Now, here's the $64 million question. Do you see that that's going to occur for all the variables? Look, I only fed back one. I have a SISO loop. This is SISO, right? Single input, single output. What if I had throttle? I didn't put throttle because this is messy enough, right? What if I had throttle? Would I change the throttle transfer functions too? Yes. I would have changed them all. All the closed loop roots change in the longitudinal set because I did this one loop closure. And did I stabilize all the roots? Didn't I not move them? Remember I said we're going to put those roots where they meet on the real axis? We took the roots, remember? The roots started out over here, and I said let's pick a gain that puts it right there. The gain for that, the K root locus was about 75. Put the roots right there. Is that only for this loop? This is the whole essence of what I've done today. I wouldn't ask you to do this. Do you see how all the roots for all the transfer functions are changed by this one? So when I stabilize this one loop with rate feedback, I've stabilized the whole airplane. So if I were then to finish up and log this down, and then I have a new del CLTF1 that's given by my root locus. So if I want to see what this CLTF is, then I use feedback, and I put QDE and then I had 75, which was the gain in the feedback loop. So that took care of it. That's all I want you to get for today. But what else did the video do? What else did the video do? If you want to watch that video again, the video then, after I closed this loop and went through S, it gave me a theta, and then it fed back a theta through the elevator through a gain, like so. do that. It closed an outer loop. And that outer loop is where we did the loop shaping. We did the loop shaping in the outer loop after I stabilized the inner loop and made all the pulls to the left hand of the plane. Now, I'm going to do that over and over and over, so I don't expect you all to see all that today. What I'd like you to get out of today is the inner loop closure stabilizes all the roots. It's done with rate feedback. I don't have to worry about generating noise because I'm going to measure it with the gyro. It's a MIMO system, but I'm just going to feedback Q and stabilize this system. After I stabilize that system, then I'm going to feedback the variable I want to control, in this case theta. I'm going to this is the variable I want to control, and that's what I did. The theta command is what I did the closed loop Bodie plot for the bandwidth. I did the loop shaping on the outer loop. Now the outer loop is often called a CAS as opposed to a SAS, and CAS means command augmentation system. Now the CAS system is something you can turn on and off in the cockpit. It's an autopilot, or it's a command following system that you use with hook up to the stick. So you turn that on and off depending on what you're doing. The inner loop always stays on. The rate feedback always stays on. You turn that on with switches before you fly. The inner loop SAS never goes off. It stabilizes the system. Because if that SAS goes off, what happens? I get unstable routes, right? For the F4. I'll be flying an unstable airplane. So this one always stays on. But the CAS I turn on and off depending on what I want to control.